Hey guys, this is my first video, and here in this video series, in this video, I'm just going to work through various data sets, tell you my thought process, how I'm working through it, and just about everything, how it goes. So for this video, we're going to work on the Boston data set, the Boston housing data set. So what I did was, in my Jupyter notebook, I set up a folder and just created now my Jupyter notebook. So the first thing I want to do whenever I start a new project is import my fundamental libraries. So the first one I'm going to import is pandas as PD. Pandas is a library for working with data and manipulation. It is built on another library which I'm going to import, which is NumPy, which is for matrix multiplication and stuff like that. So import NumPy as NP. The next one is MATLAB and Seaborn. They're used to graph out and just have just an easy way to graph. So import Seaborn as SNS, and then import matplotlib.pyplot as PLT. Alright, so now I have these four that explained how they each work. Let's start with how to load the dataset. So the dataset of the Boston dataset is actually inbuilt into sklearn, which is the library we're going to use today to just do the machine learning. So first thing is it's important in it. So from sklearn datasets import load Boston. So yeah. So then this is actually a load Boston function. So now that I have the function that gives me it, I gotta put that into a variable. So I have data equals load Boston. Alright. Boston. Alright, cool. Now let's take a look at the data. And whoops, it's a function. So this is not that favorable to work at. We can't understand the data, it's way too hard. So what I want to do now is put this into a data frame. So again, data frames, that's all with pandas. So I want to do data frame equals pd or pandas.data frame. So in here we have like this data with all our data in it. So we want to do again, so our data, that's the data we're using. Now our column names, that's going to be with feature names. So data feature names. Oops, pandas. Oops, this has to be capital. It's alright, cool. So now I have it in data frame. Let's take a look at it. So df.head. Function, my bad. Cool. Now this is a lot more favorable to look at. We know what each of these are. But in order to first start working with our data, I have to understand what the heck these all mean. So let's look up the Boston data set. Alright, so crim per capita. So now that I looked it up, crim per capita crime rate by town. That's what crim is. ZN is the residential land zone, or okay for lots, proportion on retails. Charles Dutton variable, just array, nitric oxide, average rooms, proportion of owner dwelling, weighted distance, index of radio highways. Alright, cool. Now I have just a little bit of understanding. Alright, cool. These are the different aspects and variables that work with it. So now that I have this, the first thing I always need to look at is, are there any null values that, or NA values that I need to take a look at? So df.info. Cool. Here I see, alright, we have 506 entries, and look at all of these, 506 non-nulls. That means we have no null values, there's nothing to remove, nothing to take a look, or nothing to input it. So now that we have this, let's start getting a deeper look into our data. So one thing I realized here is in DF, if we look at data, we have this. We didn't add our target variables, which is my bad. So what I want to do is now add on my target variables and my med v, which is the median of owner-occupied homes, median the value of the homes. All right. So to add a column, simple as this. and then equals data dot target. Cool. Now we added it. Now, not sorry, my bad. df. Cool. Now, look here. Now we have our target. This is now we want to do create a figure or using matplotlib. So fig is equal to plt.figure of fig size 5. I'm gonna deep by 200. Why I'm doing this is just because I want to create a heat map. So I'll show you what a heat map is. You'll figure it out. Core. So, alright. Fig size. Alright. So this is a heat map, but I don't get much from this. So what I want to do is I want to add annotation. So annote is equal to true. And this is very hard to look at. So let's figure out how do I like get this to be readable, make this text size smaller just so I can see the numbers. So I looked this up online. It's annote underscore KWS equals size 7. I figured out that was the best number. You can, it's just trial and test. And now I can see, all right, these are the correlation values. So of these, we want to create I'm just going to look at which ones are the two highest correlation values with our actual target, which is MEDV. So we see that it's this RM value and this LSAT value. So the average number of rooms, that makes sense. And LSAT, just the lower status population, sure. All right, so what I'm going to start doing now is I'm going to create my scatter plot. So sns.scatterplot. That's one of the reasons I love Seaborn. It's so easy to just create graphs. Data is equal to df, x equals lstat, right? And our y variable is equal to medv. Make sure to put your target variable as your y variable because that's your, I guess, target. So we can see here, all right, it's a non-linear pattern. So I would say maybe linear regression might not be the best fit for this one, but we're still going to try it out anyway. Scatter plot, and then data equals df, x equals rm, y equals medv. Alright, cool. Here it's more of a linear-esque kind of pattern, so we say, alright, cool. Now, what I want to do is, let's figure out, just to make it easier on my computer, because this first type of regression we're going to run is polynomial regression. So, first things first, I'm going to just get rid of the columns I really don't think make a difference. So like CHAS is a 0.18 correlation, that might not help that much. We have this, which I don't think is going to do much, B. So in my features, or my x variables, x, I set equal to df.drop. I want to drop, of course, my target, because I want only my features. I'm going to drop dis, chas, b, oh, and zn. Because you can see here, like b, there, dis 25, I don't really need that, zn 0.36. Just some variables to get rid of, just to make it easier to run on my computer. So then now, for my target variable, it's straight up just easy. Oh, one thing to not forget is on what axis to do it on. I keep forgetting that. You have to do it on axis of 1, meaning that you're going to delete the column, not the row. You're looking at the column. So now we want to take a look at our x. These are what x variables are going to work with, and this is just straight up the y variable. So this is simple as that. All right. So the first one I want to work with is polynomial regression. Cool. So now in polynomial regression, you have to add your polynomial features. So to do that, so from sklearn.preprocessing, this basically does everything for you to add the polynomial features. Like if you want to make a squared, cubed, whatever. So import polynomial features. Another thing in this is from sklearn.model selection. You'll want to import train test split from sklearn.linear, because one of the things with polynomial regression is you take your data, you make it to polynomial features, which is like you're making now an x squared or x cubed graph, and then you use linear regression on that. And then import linear regression. And then we need some way to test this data to see how well is it actually doing. So from sklearn.metrics, you want to import mean squared error, or not mean absolute. I think mean squared is a lot better because mean squared error penalizes farther ones more, while mean absolute error just shows having everything the same. Alright. So for polynomial features, there's so many degrees we can do. We can do a degree of 1, 2, 3, 4, all of that. So what we want to do first is we have to I want to test all of them. So to test all of them, I want to get the root mean squared error of a degree of 1, 2, 3, 4, and 5. So train RMSE, I'm going to create this, and test RMSE, I'll create another one. So this is a root mean squared error, and then the test root mean squared error. Cool. So now I'm going to do a for loop. So, what happened? Oops. Alright, so for degree in range of, I'm just test 1 to 10, just to get a decent number in there. Poly features equals polynomial features with degree of D. And there's also something called an include bias. We don't need that because we're going to run linear regression on it. Alright. Next, we take this poly features now that we have to some degree, and we want to fit it on our data and then transform our data. So what this does, I'll show you. So poly features dot fit transform, and then next. Cool. Yeah, poly features equals. Actually, I'm gonna make this poly converter. And that makes sense. Yeah. Whoops. All right. So now that, if let's say I had say this was just 3, right? If this were just 3 features, it would then add like 9 features to it. So, oh no. Basically, like multiplies the features together. I'm trying to think of an easy way to explain this. So if I have 3 features, right, A, B, and C, what if I'm gonna poly convert it to a second degree, it almost squares this. It's like x plus y plus z whole squared. So then I have x squared, where I take the x feature multiplied by itself, the y feature multiplied by itself, and z feature multiplied by itself. And then I'll have a xy feature where I multiply these two, a yz feature where I multiply these two, and an xz feature where I multiply those two. And so I'll have these two, and these two. So it's, yeah, it'll be 9 features because like you have your normal 3 by himself, the x squared, y squared, z squared, xy, yz, and xz. So then that's what this does. And then you run linear regression on those 9 that you have. Alright, so now that I have these fit transform, I transformed it into either one of these degrees. I want to do a train test split on my x data. So x train, x test, y train test, go to train test, not split. And in this, I want to train test split my poly features and my y variables. Test size equals 0.3, and then I can do random state equals 101. So I'm doing random state as 101 as a way to keep that constant with all my different tests of linear regression. Because by having the random state as 101, the train test split will always be the same thing for any time I run it. So if you want to have the same results as me, and if you're following along, you can just put this, and you'll have the same exact root mean squared errors as I get. So now it's time to create the model. So for this model, we're testing, we're going to use linear regression on polynomial features. So, linear regression. All right. So now we have our model. It's an empty model though, so we have to fit it on our data or train it on our data. So model dot fit, and I want to fit it on my X train and my Y train. Cool. So now that I have this done, I have a model, this, a fit and train on my X train, Y train. This is time we do a train predictions, and that's model dot predict X train, and then test prediction is equal to model dot predict on Y train, Y X test. All right. So, if whoops, not from. I don't know where I got that. For D in range. All right. So with these, why am I actually testing it or predicting on my X train if I tested on my X train or fitted on my X train? So I'm doing this as a way to see at what degree am I starting to overfit. I'll explain more when we have the graph. But if I have a degree of like 10, I have a very high chance of overfitting with the data where I have basically a model which only can get the training data, but doesn't get the actual trend of the data. I'll show you this you'll see when it starts to overfit, the test data is going to just jump up. The test RMSE is going to stay up, just jump, while the train, like root mean squared error, is going to it's still going to go like almost to zero, where it just basically hit every point. So now I want to upload these or append these and np.square root because I'm doing root mean squared error, and this just has a metric of mean squared error. By taking the square root of it, it's more easy, I guess, to understand what that number means because it's in the same units as your features now, or as your label. So, all right, np.square root mean squared error of y train, train predictions. And then I can just copy and paste this line. Y test predictions. Cool. Make sure, alright, cool. Test alright. Sorry, I just forget to capitalize it. What the heck? That's not true. Predict. Oh. Alright, this should be all the errors. Alright, cool. It's going to take a bit of a while. This is our now training of it. So cool, it's done. Now at this point, we want to plot it. So I'm going to do, there's plt.plot on the range of 1 to 10. I want to plot, for first I'm going to plot my train RMSE data, and then I'm going to label it, label equals train RMSE. Alright, and it's going to be the same thing with my test root mean squared error. Just to add a little bit more to my data so I can actually easily see what I'm looking at. And then plt.legend, just to add the legend in there. So I run this. Alright, so what we can see from this data, we know this range is pretty high. So we can see, all right, somewhere around 3, 2 to 3, it's starting to overfit. So what I can do is, okay, so this to the range of 1 to 4. Actually, no, 1 to 3. So this is just a way to zoom in. You can either do it like this, or if you want, I can do it like that, where you can go plt.xlim from 2 to 4. So now it's zoomed on this part, and I say, all right, cool. I want to go more from 2 to 3. And then I guess I have to go ylim, plt.ylim from, I think, 0 to 10. I'll go from 0 to 3, actually. I don't know. I'm going 2 to 3. 1 to 3. My bad. Alright. Cool. What we see here is it's starting to straight up overfit right after I start increasing past 2. So I can either do 1. Actually, I'll just straight up go. I'll go for 2. I'll just say, alright, cool. I think 2 is the best. So I can either rerun this whole data again with the degree of 2, or because I know the test RMSE when the degree is 2, I think I can just go like that, and bam, that is our testing root mean squared error at a polynomial degree of 2. Alright, but this is not the end. We want to test out now another type of model. So another one I wanted to test out was Adiboost. Adiboost is a type of, or Adiboost regression is a type of model that uses weak learners or very weak models and has a decision of all of them, has weightage values on each of their decisions to create a stronger model in the end. It's just a bunch of weak learners to create it. It's almost like 3 minds working it together is stronger than 1 mind by itself. That kind of idea. So from here, I'm going to re-import everything just so it's easier to look at. I'm going to have all this code in the description in my Discord. Not Discord, GitHub. So from the Adiboost regression, from sklearn.ensemble, because it's an ensemble of models. Oh, yeah. I want to import Adiboost regressor. Alright. From sklearn.model selection, import train test split, and then from sklearn.metrics, import mean squared error, mean squared error. Alright. Now I have these 3 here. Let's start to train test split the data. Oops. Alright, we'll start to train test split the data. Did I have the, yeah, I have the XY here, just now to make sure. Alright, so X test, X train, whoa, X train, X test, Y train, Y test is equal to train test split. The data again is X, Y, test size is equal to 0.3, and then I want my random state to be 101. Again, so you see 101, so it doesn't just mess up. And it has it, so it's like the train test split is equal with every type of model that I'm going to build today. So now effectively split. So for Adiboost regression, one of the things I want to test is how many weak learners do I want to get the best model and to be like, so my computer doesn't straight up blow up by having 1,000 models, and so it does not overfit. So to do this, I want to have a thing called errors. So for WM in range from 1 to 100. I'm going to test from 1 to 100 models. This is just the number of weak models. WM, weak models. I want to have model equals Adiboost regressor and estimators, which is just the number of weak models, and also got the weak models. Cool. Take this model, model.fit, x train, y train, easy as that. Now it's fitted on the data. Here I can make my prediction. So pred equals model dot predict on my x test, and then errors out of pen means np dot square root means squared error of y test and pred. Cool. Have this run for a bit, and then we can figure out which model or how many weak models makes this whole model work the best. Cool, it's done. So again, plt.plot, this is matplotlib, so my x, I want to go from range of 1 to 100, and just some errors. Plt.x label, number of estimators, plt.y label, error, that's it. Oh, we go wrong. One second. Cannot figure out why this error is. I'll just remove it. That's weird. Alright. I didn't have that hard. Alright, but what we can see is, alright, it hits a low point of errors around 20. Right? So then I can do plt.xlim from, I think, what I'll need is 15 to 20. Just as a good range. Alright, cool. Alright, I think from here I can see that 18 models, that's the hit right there. So 18 models is the way to go. And you know what, for this round, I'm going to just refit it on the data. So next, just have all of these. Put it here, this 18 model.fit, x test, and then I just do not need to do this. Actually, I'll just print it out. Alright, whoops. Cool, and now I see our error is 4.56. So what we can see is a little bit less or a little bit worse than polynomial regression, but it's fine. Let's try our, I think, third, the next one which I'll try doing, which is an SVM regressor. So an SVM does something a little bit different. So what it does is it draws, well, an SVM itself just draws hyperplanes to separate data. Not really sure how the regressor works, but I know how the classifier works, and that's how the classifier works. But one thing that's good with, as long as you have, I guess, a basic idea, like this one, it uses like lines and separates the data somehow, and I guess that's usually how it classifies based on if it's in this side or that side. But I guess it maybe uses one of those ideas for regression. So it's fine if it doesn't figure out really how it works. A lot of the models you won't realize like what it does all the way in the back end. But one thing good with sklearn is it makes it so all the code is almost the same. Like for this code can be used with almost any model. All I'm doing is just clearing up the data, seeing what I want, what I don't want. And then it's nothing data specific. I'm just setting the test size, training it, looking at it. All right, and then graphing it. And then now Adiboost regression, same thing. And it'll be the same thing for SVM regressors. So for an SVM regressor, I want to import, I think, a few things. So the first thing I want to do, of course, sklearn model selection. I'm going to import this again just so it's easier to look at if you're looking in my GitHub. And you want to take a look at that. Import train test split. Next, so one thing about I want to do is I want to scale the data. Now, this is the first one in this that we're actually scaling it. So let's look at why I'm scaling it. So if we go back up to our data, you can see here we have ZN or CRIM, right? I'm keeping CRIM. That's at 0.0632, right? It's just a small number. And then I have taxes, which is like 246, or B, which is 396. These are so much greater than CRIM that it makes it a lot slower to train, a lot bigger numbers for CRIM. So what I'm doing is saying, nope, I'm going to take all of that, make it a standard scaler. What a standard scaler puts it into what is called z-scores. Basically moving the mean, let's say if the mean of the data is 100, it somehow moves the mean to 0 and makes it so that I think the standard deviation is 1. So it's like all between 0 and 1. And what this does is it helps, I guess, standardize the data, make it all one range of numbers, all closer together, and all in like the same units. Because z-scores, which is what standard scaler does, it has no units. It's unitless, which is very good for, I guess, machine learning. One thing with this, though, is if you want to add new data, or you want to predict some new data that comes in, you're going to have to use standard scaler on that data before you put it into the model. So then another thing with this is I want to import the actual model we're looking at. So from sklearn.svm support vector machine, I want to import svr support vector regressor. All right, so another thing I want to do is from sklearn.metrics import mean squared error. All right. And now I want to try something different for this because SPRs have a lot of different hyperparameters. And machine learning is all about tuning these hyperparameters to get the best model for the data. And to do that, I want to try two things. I'm going to do something called a pipeline and using grid search VR, which uses cross-validation to, I guess, check these different hyperparameters. So I want to import first grid search, so from sklearn.model selection, import grid search CV. You can just press tab and it'll figure it out. And then from sklearn.pipeline, import make pipeline. I'll explain it while I'm coding what a pipeline is. So the first part of the data, what I want to do is I want to train test split. So x train, comma y x test, comma y train, comma y test equals train test split on my x y data, test size equals 0.3, and I want my random state to equal 101. Alright, so now again, standardizing the train test split for all these models so I can truly see which one does the best and not having the train test split of them be different. Because sometimes your train test split can be very good in helping you out to get the trend of the data. Other times it might mess you up a lot. Alright, so first thing I want to do is I want to create what is the grid model, the grid search model. So Grid is equal to grid search CV, which uses grid search CV. So the first thing I want to do for grid search CV, it uses cross validation to just see the different hyperparameters. So first thing I want to do, what is my estimator? An estimator is just what model you're building it on. Here I'm building on SVR, so estimator equals SVR. Sick. All right. Next thing, I have to have a parameter grid. What is the parameter grid you're asking? Cool. So SVR, if we take a look here, SVR. All right, svm.svr. Here I have kernel, what degree of polynomial regression, some gamma value. We have some C values, which are regularization parameters, to see what kind of penalty on the slope. If this one, it's using L2 penalty, which, if I remember correctly, is lasso regression, or like lasso. And then, yeah, we have all of these that we want to test. So if we go back here, we want to first, in our param grid, we can set, nope, wrong go. So our C values. I have some C values already chosen out. So 0.01 I want to test, 0.1, 1, 5, 10, 100, and 1,000. Next thing, I want to have my gamma values. So it's just the type of almost learning this auto. Oh, god damn it. And scale. Next, that's actually it. That's the things I want to test. Here, let's just look. So this is, I'm changing these 2 degrees, not these. The degree I'm setting is 3. I can test different degrees. I'll keep it as 3 actually. Or I can do more. So I'm changing this one and my regularization parameter. Next things up, I want to take a night of scoring, because how is the grid search going to figure out which of these combination is the best one? So in this grid search CV, I want to say scoring equals neg mean squared regression. Mean squared error, my bad. Alright. So earlier we're using mean squared error. Now we're doing negative mean squared error. Why is that? Just basically, it's just for a grid search, it just wants the highest value, and by highest error, whatever highest value is. And so by having a negative, the better scoring one is basically just higher. 1 second. Alright, so I got my scoring done, and then next, just to have a little bit of information, there's something called verbose, and I'm going to set that to 2. Basically, there's only 1, 2, and 3. 1 gives you the least amount of information, 2 gives you a little bit of information about the testing and trying, and 3 gives you the most. So you can just look at it printing. Alright, next, I want to create my pipeline. So, first things first, pipe equals make pipeline. So what a pipeline does is just an order of like steps. So the first thing I want to do in the pipeline is standardize my data. To standardize my data, I run standard scalar on it. Done. Next, I want to which model am I running it on? Now I have the standard data, standardized data. I want to put into a model. What model? We created that model right there, the grid model. Cool. I have this. Now pipe is my model. And what I do with pipe is I pipe.fit x train y train. You'll see what happens. So you can see here, see what happened. This is the C value it's testing, the gamma value it's testing, and the time it took. And it keeps going. So now it takes it at 5 times on auto, 5 times with scale. And then now it changed from 0.01 to 0.1. It tests every single combination of all the parameters I gave it. So now that we've created this, we have our pipe model. Preds is equal to pipe dot. Actually, no. how do I check? I have this. How do I check what exactly where's the best out of this, right? So to do that, I do pipe.best estimator underscore best estimator. Pipeline has no. Sorry, I do grid because it builds it on that model. So in my grid model, it built everything. So my grid.best estimator was where the C value is 100 and my gamma is auto. Cool. That's just good to know. Now, what I'll do is I can check my root mean squared error value. So to do this, I can do grid dot or pipe or pipe that's a preds equals pipe dot predict. You can also do grid dot predict. So predict x test, and then I can just straight up do RMSC. I can just, no, I don't need to do that. I can just do np dot square root of mean squared error of y test comma preds. So y test predictions, cool. Now we can see 3.51. So these are the three I'm trying now, which was SVM, regressor, Adiboost regression, and polynomial regression. So of these, we can see here we have a 4.42 root mean squared error. Here we have a 4.56 root mean squared error. And the last one, we have a 3.51 root mean squared error. Of these, we can see, all right, our support vector regression model is the best one. We've got our estimators here. Now let's create our final model and get it ready for deployment. So we have here, let's start building final model. So now we want to build the final model and just straight deploy it. So what the testing data does for us is it tells you how good your model is. But when you want to deploy your model, you want to train it on everything. We've got the best model we have. We've got the best hyperparameters we have. Now we want to use all the data we have to train it to become the best model it can be. Right? So what we want to do is create a function called final model. Make it a support vector regression. We can take our hyperparameters from here. So my C value, which is my regularization parameter, set it to 100. And then my gamma value, I can set it up equals to auto. Auto. So here, we have that done. Now to actually not deploy, but like almost save this model, I use a library called joblib. So import joblib. So now that I have that, I can easily just do joblib dot dump final model, comma, I'll call it final Boston model dot pkl or dot pickle. Cool. And I want to do joblib dot dump. I want to just dump my column. So if someone to, just so it's easier to understand, because I want to have my data there. So Boston column names dot pickle. Cool. Bam. Saved. I've got my column name saved. I got my final model saved. Now I'll just show you a little bit on saving your final or loading your final model. Nope, I don't want to make this mark down. So for loading the model, I do call names equals joblib.load Boston column names.pkl. Right, and here it's there. We put it. Bam. these are the columns we used. Right. Next, we want our loaded model. Loaded model equals job load, and then final Boston model PKL. And now, if you were to, let's say, predict something, I would say loaded model dot predict, and blah blah blah. And as you can see, it saved it. That's why I created the folder beforehand. So now it's saved both the column names and the final Boston model all in this. So that's done. We figured out, all right, support vector. What we did in this whole thing was we first imported our main libraries, loaded the data, made into a data frame so it's easier to work with. Just did some data manipulation, just looked at the data, took what we wanted, what we didn't want, got some information about the linearity of these. Ran a polynomial regression, Adiboost regression, SVM regression on this data, figured out SVM regression was the best model, and from all of that, we built the final model and then saved it. I hope you guys learned a lot. I'll see you guys in the next video. See ya.